So just do the 2nd of September. That's when we're on Labor Day.
Yep.
Let's do on Labor Day.
So the homework sets are Sunday at midnight.
Oh,
They're
right,
like an online
forgot.
turn-in, and Monday is, we don't have school on Monday, so just Monday at midnight this week.
Right.
So that's why. But it wasn't an accident.
All right.
So today, 2.1, we're going to talk about the idea of a radian. So when we describe an angle and we want to measure that angle, typically we use degrees, right? You know, it's 45 degrees or 30 degrees or 18.6 degrees. But that's not the only way we can measure an angle. There's another measurement that we use called a radian. So let's start by just describing what we really mean by that, right? So let's say that we have some angle, right? And let's make the vertex of that angle the center of a circle. And let's say that circle has radius 1. Everybody feel okay with this idea? The circle has radius 1. The length of its radius is 1 unit long. Is that?
Yeah.
Okay. So this distance, that arc length, is the measurement in radians. So this radian measure is like a distance, like it's something you could measure with like a tape measure or something. It'd have to be like, not like a measuring tape, but like a, you know what I mean, like a string or something you could use. Is that okay? So it's just a new way of defining like how big an angle is, where it's based on that distance now. Is everybody okay with that? So we have these two different ways of measuring an angle. We have degrees and radians. Whenever you have two different ways of measuring something, what are you going to want to go, or what are you going to want? Well, if you have like feet and inches, what do you want between those? You want like a conversion factor, right? A way to move back and forth between the two, right? If we have degrees and radians, we want to know how I can take a radian measure and turn it into degrees, or a degree measure and turn it into radians, right? Everybody's cool with that plan? So what we're going to do next is we're going to come up with a conversion factor. Like what is, like there's 12 inches in a foot. How many radians are there in a degree or something like that, right? Everybody's cool with the plan? Okay. So this is what we did, or what we do. We're going to start with a circle with radius 1. And we're going to look at a 180 degree angle. So the radian measure for that 180 degree angle will be the same as that green distance, right? So if I look at that green distance, that's like half of the circle circumference, right? Does anybody remember the formula for the circumference of a circle? It's been a long time. 2 pi r. And in our circle in particular that we've drawn here, the radius is 1. So when I multiply that out, I get that 180 degrees is equal to pi, and well, let's actually say.
Is that an R after the pi on the second line?
Yep. So 180 degrees is pi radians. That's our conversion factor. 1 inch is 2.54 centimeters. 180 degrees is pi radians. That's our conversion factor. So far, so good? All right. Let's do a little practice making that conversion. So, you guys remember in your chemistry? Yes, sir.
Just real quick, sorry.
It's okay.
That's in the conversion factor, that's an R times D.
That's radians, RAD. That's just an abbreviation. No problem. Again, I recognize that I have less than spectacular handwriting at time. If you're not sure, feel free to ask. I know many of us are in the same boat of like, I can't even read what I wrote. I mean, I can read my own writing, but, I get it. All right. So the first set of examples, we're going to be asked to convert back and forth from degrees to radians. So you guys remember in like your chemistry class where you want to convert from like mass of a substance to like moles or something? That process uses like dimensional analysis where you multiply by the conversion factors and stuff. Stoichiometry, sure. We do that same kind of dimensional analysis here to convert. So if I want to convert 90 degrees to radians, I'm going to start with like 90 degrees. And I remember that the unit up top needs to match the unit in the bottom. So I know the 180 degrees is going to go down there. And the pi radians will go on top. Is everybody cool with how I knew how to arrange my conversion factor? So I know radians and degrees and degrees are going to cancel. So when I multiply this out, I'm going to get like 90 pi over 180. And what do you notice about this fraction? Can we do anything with this, Roman? Yeah, so the 90 over 180 can reduce. So we'd have pi over 2 left, right? 90 divided by 180 is 1/2 radians. And that's our final answer. Now, if the directions asked you for an approximate answer, you could type that into your calculator and get the decimal out of it, right? It's like 1.57 if you chose to do that. But in general, radians, we prefer to leave our answers exact as much as possible, right? We'll look at an instance in where it's not really practical to do that, but all right, let's do the next one. It says, convert 152 degrees to radians. So that's going to be the same unit conversion. So I just copy the same conversion factor. Degrees and degrees cancel. And just like before, let's try to reduce the 152 over 180. That's a much harder reducing problem though, right? So I recognize it can reduce because 152 and 180 are both even. So definitely there's a factor of 2 in there. If I divide both of them by 2, I get 76 over 90. Both of those are still even. So I'll do it again, and I get 38 over 45, and I think that's as far as I can go. It's a little less appetizing fraction than 1/2, 38 over 45. Wouldn't be incorrect here, again, depending on the directions, where they ask for an exact value or not, or an answer in terms of pi or not. To convert this into a decimal again, if I type that into my calculator, I get like 2.65. Again, just depends on the directions, whether you're required to give your answer exact or in terms of pi, or rounded, right? The direction should tell you what is required of you. And if nothing is mentioned there, then, like either would be appropriate. Is everybody okay so far? No big deal? So if I look at the next one, now it says to convert 2 pi over 5 radians to degrees. So this time, since radians is in the top, I know radians are going to be in the bottom. So I have that conversion factor will be flipped upside down. I'll have 180 over pi radians this time. Still okay, everybody? So I can reduce the radians, the unit. But I also notice, what else can I reduce here? The pies, yeah. If you know it, just shout it out. You don't have to raise your hand if you got it. No big deal. You can do that too, though, if that's how you like to, raising your hand is fine, of course. So if I do that, I get 360 over 5, which is 72, I think. How do you do that fast? Well, I don't do the long division. I think of, calc. I do 360 degrees, or 360 is the same thing as 36 times 10, right? 10 divided by 5 is easy, that's 2. And then 2 times 36, that's pretty easy, that's 72. So that's just mental math, how you do the mental math quickly. You don't try to do the long division problem, make it an easy problem, Are you required to do mental math at any point in this class? No. I'm just just talking through how you can do it, because some of us are kind of impressed by simple tasks, how did you do that so fast? Well, this is the way I thought about it, It's math class. All right, the last one says 1.6 radians to degrees. So again, we'll do the same thing. I'm going to use that same conversion factor from before, because this problem is also radians to degrees. And here, I guess I could multiply this out. What does that got to be? 288, I think, over pi. Yuckarooskies, though, because we're talking degrees. Does anybody ever give you, would I ever tell you 288 over pi degrees? Goodness gracious, no one's going to say that. We'd probably just type that into our calculator and give it a decimal. Right? Degrees, we have no problem making a decimal. That's what we're used to. Yes, sir?
So that 288 over 5 is fine, but it's easier.
Yeah. I mean, just you're not going to see a problem where it's 288 over pi degrees, right? We just make them decimals. That's kind of the convention. It's fine. It's not wrong. What do you guys think so far? Piece of cake, no big deal. Good. So the next thing we're going to talk about is calculating arc length. So if I have part of a circle and I want to find out what the length of that part of the circle is, I'm going to use my arc length formula. And there's two different versions. So the first arc length formula is S equals R theta, where S is the arc length, R is the radius of the circle that your angle is inscribed in, and theta is the measure of that, that central angle, where theta is measured in radians. Now we have an alternate formula, S equals pi r theta over 180 degrees. S is still arc length, R is still radius of the circle, theta is still the central angle. The only difference here is that in this case, theta is measured in degrees. So I have a degree version of the formula and a radian version of the formula. Could you just use the same formula every time and convert your angle? Sure. You know, like could I always use S equals R theta and just convert all my angles into radians if they weren't already in radians? Sure. And in fact, that's all that second formula is the first formula multiplied by pi over 180. So let's do a little bit of practice using that, or using those formulas anyways. So first example says solve for S if R is 1.4 meters and theta is 0.98 radians. So the key here for me is what unit is that central angle measured in? Because that central angle is measured in radians. I know I want to use that version of my formula. So if I plug in now for R, 1.4, and theta, 0.98. When I type that into my calculator, I get 1.372. Not in radians. It's going to be measured in the same unit that the radius is measured, because S is a length.
Oh,
So this should be meters. Yeah, exactly. Good. That would have been the next question, is what unit should we write this as? And you were already wanting to see what I was missing there. Very good. All right, if I look at part B, solve for S if R is 3.8 inches and theta is 40 degrees. I notice because I'm in degrees, this time I'm going to use the other version. So I'll plug in my R and my theta. And then I'll type this into my calculator. Now, to get this into my calculator, I want to show you guys something. Whenever I have like a calculation that involves kind of a complicated looking fraction, your calculator you can type this into your calculator exactly like it looks on your sheet of paper, so you don't have to muck around with any parentheses. To get that horizontal fraction bar into your calculator, you can press the alpha button, that's the green one here on the left-hand side. The y equals button, that opens up the fractions menu. If you pick the first command, that's the horizontal fraction bar. So you can type this in, oops, that wasn't pi, that was pi. Exactly like it looks on your sheet of paper, which can be a little bit safer than trying to get it in with the division symbol, because you probably run into cases like that where you meant to do something with a fraction but use the division symbol, but like you mucked up the parentheses and got the wrong answer out of it. If you use that horizontal fraction bar, it can just type into your calculator just like it looks like on your sheet of paper and save you the aggravation of like trying to figure out if they put the parentheses in the right spots. And I like that. Like let's keep it simple, right? So I get 2.653 maybe. And the unit here should be inches, because it should match the unit on the radius, right? So far, so good. Again, should be pretty easy. We're just kind of, like using a formula. Last example, so it says solve for r. Notice we're looking for a different variable. If s is 18 centimeters and theta is 2.31 radians. So since it's radians, I know I'm going to be using the radian formula. And then let's plug some stuff in. So s is 18. R is what I'm looking for. And theta is 2.13. So to solve for r, what do I need to do? Okay. By doing? Divide by 2.13. And again, I'll just type that into my calculator to get 8.451. And the unit here should be centimeters. It should match the unit of the arc length from the question. So the R and the S should always have the same unit. So pretty straightforward, right? We're just basically plugging stuff into the formula and doing like some algebra 1 algebra to find the piece we're missing. NBD? Feels like NBD, right? Can this get any, can it get any harder? Well, not a lot harder, but like, let's look at some other kinds of examples. So this next one says, find the perimeter of a sector with a central angle of 1.7 radians cut from a circle of 5 centimeters. Or I'm sorry, circle with radius of 5 centimeters. Probably the question is here, like, who remembers what a sector looks like from geometry? What is a sector? Yeah, it's like a slice of pizza, right? So like if you have your round pizza, not the Detroit style pizza, the round pizza, and it's cut up into, 8 slices or whatever, each slice would be a sector. Everybody's cool? Very good. So a sector, kind of looks like this, right? So each of the straight sides of our sector is a radius. The curved side is the arc length. And that central angle, the angle in our sector, is the central angle. So given to me in the problem, I know that the radii are both 5. The central angle is 1.7. And I just need to solve for S, right? That arc length. Because to find the perimeter, that's just going to be the distance around that figure. So I have R plus S. So it basically just comes down to solve for S like we just did in all those previous problems, right? Oh, okay. Well, since we're in radians, what version of S are we going to be using? Well, the R theta version, right? So the unit absolutely will be in centimeters. Yes, for sure. And so now if I do the perimeter, I have 5 plus 5 plus 8.5. So 18.5 centimeters. Does that feel okay? Pace is okay, I'm not going too fast. It's all right. Make sure I'm not leaving anybody behind. Okay. My last example for this section is probably the most difficult thing that we'll do in this section, but it's basically just a big unit conversion problem. So this says a car has 18-inch diameter tires on it. If the car is traveling at 15 miles per hour, how many revolutions per second are the tires making? So when I read this, look, come on. It's basically I want to turn this from miles per hour into revolutions per second, right? That's basically what it's asking me to do. Does everybody kind of see that it's just a unit conversion problem? So we'll do that. We'll start with what we know. So 15 miles per hour is the same as 15 miles per 1 hour. And I know that I want to end in revolutions per second. I don't know how to convert miles to revolutions immediately, but I sure as heck know how to convert hours to seconds. So let's start with that. Does anybody remember how many seconds are in an hour? Well, that's minutes, right? There's 60 minutes in an hour. Let's do that then. So 1 hour is 60 minutes. And then I know that in 1 minute, there's 60 seconds. Or if you remembered, there was 3,600 seconds in 1 hour. You could have written it in one step too. That's okay. Is everybody okay? And we're remembering that, like, our units need to be diagonal from one another, right? You guys remember that from your chemistry class or whatever? You did unit conversions before? Probably some science class, right? So if we just take a brief pause here and look at where we're at. We're in miles per second, right? That's what we've done now. Everybody see that? Well, the seconds is good. That's where we need to end up on the denominator. But now we need to turn this miles, this linear distance of miles, somehow into seconds. And the piece that we're going to need to do that is going to be the diameter of the tire. Somehow that's going to end up giving us the way to convert miles into revolutions. Now, when I look at that 18-inch diameter tires and 15 miles, can somebody grab the door? What do we notice? Anthony? They're both lengths. What do you notice about the length unit, though? I have 1 in miles and 1 in inches. They're different, right? Is that going to be a problem? Yeah. So guess what I'm going to do first? Convert them to the same thing, right? Let's convert miles to inches. It's usually easier to go that way than inches to miles. Now, does anybody remember how many inches are in a mile? No. Does anybody remember any things that are in the mile?
2,000.
It's 5,280 feet in a mile. That's, I think, what you're searching for. Now, I wouldn't expect you to remember that. And then how many feet are in an inch? Or how many inches are in a feet? 12. I would expect you to remember that. So if we look now, miles and miles have canceled, feet and feet, and we're left in inches per second. Now what we want to do is somehow figure out that relationship between linear distance and revolution. So I need to figure out how far linear does a tire go 1 spin around. It's going to be what? Ooh, you're very close. Very, very close. Think about it this way. So we have like our wheel here, right? And let's say this is the point that's like starting on the ground. And let's say we put like a piece of sticky 2-sided tape on the wheel. That as it rolls along the ground, that tape is going to stick to the ground and not to the wheel anymore, right? So as the wheel goes, it's laying that tape along the ground. And once it's completed 1 revolution, all the tape that was on the perimeter or the circumference of the tire is now laid down on the ground, right? How long is that tape that's on the ground? It's the circumference of the wheel, right? Look at the green tape when it's around the wheel. How long is that green tape? Well, it's the circumference. If we laid that exact same tape down onto the ground, how long is it this way? Well, it's still the circumference, right? So that's our conversion factor, is that 1 revolution is equal to 1 circumference. So in our case, remember, circumference is 2 pi r. What is the r for our tire? Radius. So how long? What number? 9, right? We remember radius is half of a diameter, or diameter is twice the radius. Either way is fine. And now what we have is revolutions per second, right? Everybody's good? The units match? They're what we were asked for. Now what we got to do is punch the numbers through on our calculator. This is an excellent opportunity to practice using that horizontal fraction bar on our calculator, right? It'll make this life much easier. So I'm going to do alpha, y equals, and then pick option 1. And in the top, I'm going to do, well, I'm going to ignore all the 1s, right? Because if I multiply by 1, that doesn't really do anything. So I'll do 15 times 5,280, and then times 12. And on bottom, I'll do 60 times 60 times 2 pi times 9. So I get 4.669 revolutions per second. That's probably about as bad as it gets for this homework set. Which again, once you've seen it gone through, you know, it's not so bad, right? Like, it just turns into essentially a unit conversion problem where this piece is that's the key to kind of unlocking any revolutions problem. Max?
And then, like, how many like decimal places on average should we stop?
If the directions don't tell you, usually 3 is fine.
All right.
Yeah, if the directions don't tell you what to do, 3 should be fine. But that's one of those things, like, depends on the directions. You know what I mean? All right. That's it for section 2.1. For section 2.2, we're going to be doing the same right triangle stuff that we practiced the first day of class with a couple of small additions. Okay? Addition 1, angles might be in radians. All right, whatever, no big deal. Addition 2, if you notice that, like, so sine is opposite over hypotenuse and cosine is adjacent over hypotenuse and tangent is opposite over adjacent, but we don't have a function for, like, hypotenuse over opposite, right? We do now. Yes, sir. Yeah, go ahead. So that's the first order of business here in section 2.2, is we're going to define 3 new trig functions so that we have all the possible combinations with opposite adjacent hypotenuse. So our 3 new trig functions are cosecant, which we abbreviate as CSC. Cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. We abbreviate that as SEC. And adjacent over opposite is cotangent. We abbreviate that as COT. If I look at the definition for sine and cosecant, do you notice anything about those 2 definitions? Great. When we say things are flipped in mathematics, we have a special term for that. It starts with an R. Reciprocals. Yep, exactly right. What about cosine and secant? They're reciprocals. And tangent and cotangent? Reciprocals again. So when it comes to me memorizing the definitions for cosecant, secant, and cotangent, I'm not memorizing a new definition. I'm just remembering that cosecant is the reciprocal for sine, and I know the definition for sine, so I can flip it really easy. I remember secant is the reciprocal of cosine. I know cosine's definition, so, and cotangent is the reciprocal for tangent. Everybody's cool? Now, should be really easy to remember that tangent and cotangent are the pair that are reciprocals because they both have the word tangent in them. The tricky part is remembering whether cosecant goes with sine or cosine. The way I remembered that is that no cos go together. So cosecant does not go with cosine. Has to go with sine. That was the way that I remembered it when I was doing this for the first time. Everybody cool on these three new definitions? No big deal, right? It's just like sine, cos. If I can do sine, cosine, and tangent, I can do these three. It doesn't make a bunch of difference there. So let's do an example. So it says here, find the exact values for all 6 trigonometric ratios for theta in the right triangle. So what I'm going to do is I'm going to just start by writing down the 6 ratios and their definitions. So I'll say sine theta is opposite over hypotenuse. Cosecant theta is hypotenuse over opposite, etc., right? I'm not going to read these as I write them because it just makes it harder to write. If you ever notice that when you try talking and writing at the same time, you end up just writing what you're saying and not what you need to be writing down. It's super annoying. Now, as a teacher, I've gotten good at writing and talking, but it's still like kind of a hassle or whatever. So I'll start just by writing down my definitions for sine, cosine, tangent, cosecant, secant, cotangent. All right. So if I go and I look at my triangle, let's start with sine. What is opposite? No, but I mean, like, sine is opposite over hypotenuse, right? What goes in the opposite spot? 5. Great. And what is the hypotenuse? Well, it's not written down, is it? Can we find it? How? You got a right triangle, and 2 of the 3 sides. Pythagorean theorem. Right. So before we can finish this, we have to take a little break and do the Pythagorean theorem to find that hypotenuse. So the Pythagorean theorem is a squared plus b squared plus c squared. One of those 3 letters, a, b, and c, is special. Which one is a special letter? C. What is special about C? It has to be the hypotenuse. The legs can go either A or B, it doesn't matter, but the hypotenuse must be C. Everybody's good? Okay. So I have, say, 2 squared plus 5 squared equals C squared. 2 squared is 4. 5 squared is 25. 4 plus 25 is 29, and then we'll square root both sides to get rid of the squared off the C. So that's my hypotenuse. Everybody okay with how we did that? Does that answer look okay? No, what don't we like about this answer? Yeah, we have that radical in the denominator. How do we take care of that? Yeah, good. Multiply the top and bottom of that fraction by square root 29. So remember, when we have a number outside a radical times a number inside the radical, they can't multiply together. We just stick them next to each other. So the top is just 5 square root 29. And what do we get when we do square root 29 times square root 29? You just get 29, right? Regular 29. So there is our answer there. 5 square root 29 over 29. Let's do cosecant next. What do we remember about cosecant and sine? They're reciprocals. Now, here's the catch. If I take my answer for sine and I flip it, what's going to be the matter? We end up with a radical in the denominator again. Ugh. But what if we take this answer before we rationalize the denominator? What if we take that one and flip it? Yeah. So let's do that, right? Let's not make more work for ourselves. And that can just be our final answer. So I highlighted what I ended up using to flip, right? I always like to take the non-rationalized answer to do my flipping. Yes, sir. Of course. All right. What's cosine going to be? Adjacent over hypotenuse. What over what? Yeah, for cosine. 2 over square root 29. Yeah. Actually, let's write that in up here. That probably makes it easier to see that. Oh, that's a bad throw. I'm a math teacher, not a quarterback. All right. Same problem, though, right? Who can tell me what the result is without showing the work? When we rationalize 2 over the square root of 29, what do we get? When we rationalize that denominator. Can we do it without writing any more down? So we have 2 square root 29 over 29, right? If you can't do that without writing it down, by all means, write it down. But if you're good, like we did it once, I'm going to kind of shortcut through some of the work just so the notes don't take a million trillion years. After we've done like, it's the same steps with just different numbers kind of thing. But again, if you're like, I actually would like to see that again, you're free to ask. I'm happy to do it. But this is, trying to save time in class so that we can get through more stuff and I can do more example and that kind of thing. You know what I mean? Cutting out some of the trivial detail after we've done it once or twice. All right. Secant. How's that related to cosine? Opposite means negative in math. You mean reciprocal? I know what you mean, but that's not what you said. I'm just trying to clean up our vocab. No big deal. I appreciate the participation, though. Okay. So which one should I do the flipping with? The final answer or the starting? Yeah, the start here, right? Let's flip this guy because no rationalizing the denominator needed, right? Everybody cool with the reasoning there? Okay. What's the answer for tangent? What over what? 5 over 2. Nothing need to be cleaned up there. How about cotangent then? What's that? 2 over 5. Excellent. And again, that was just, flipped it. Everybody's okay with what I'm doing here? Circling the final answers and I'm highlighting what I used to get the other one. It's no big deal, right? Not bad. All right. Let's do another example of something similar. This one says, let theta be an acute angle of a right triangle. If sine theta equals 1/3, find the values of the other 5 trigonometric ratios for angle theta. So you read this, and this sounds like a different problem than the first one. Everybody sounds very different, right? The wording's very different. What it's giving you is different. It's the same problem. The difference is that they didn't give you the triangle. Here we have to build our own triangle. But once after we've done that, it's the exact same problem. So let's see how we build the triangle. Yeah? Okay. I'm going to start by just drawing a picture of a right triangle, and just to emphasize that this is the same problem really as the first one. I'm going to draw my triangle exactly like I drew had the triangle drawn in the first problem. So, relative to the angle theta, this side was opposite, this side was adjacent, this side is hypotenuse, right? Everybody agree? In the problem, we're told that sine theta is 1/3. Well, I know that sine is opposite over hypotenuse, correct? So I know that the opposite must be 1, and the hypotenuse must be 3. Everybody okay with how I used sine theta equals 1/3 to figure out 2 of the side lengths for my right triangle? Still need to figure out what adjacent is. How do I do that? Pythagorean theory, very good. So the equation a squared plus b squared equals c squared. What do I fill in? Okay, what is c? Okay, so I have 1 squared. I'll write b equals 3 squared. So 1 squared is just 1. If I subtract that from both sides, I have 3 squared or 9 minus 1, that's 8, right? And then I'll square root both sides. When you see the square root of 8, hopefully you recognize that's a radical that we can simplify. Did you guys see that? Do you remember how to simplify radicals? What I want to do with that square root 8 is I want to break it up into factors that are perfect squares. So for example, I know that 8 is 4 times 2. So the square root of 8 can be the square root of 4 times the square root of 2. And I know the square root of 4 is just 2. So I can do that. Everybody happy with how I've done that? So far, so good? Now, this is now ostensibly the same problem as the previous one. I'm going to do one pair of ratios rather than all 6 of them. I'm going to do cosine and secant, just so that we see that rationalizing the denominator piece again. So cosine theta, that's adjacent over hypotenuse. So that's 2 root 2 over 3, right? That's perfect just the way it is. So I won't do anything there. Secant is the reciprocal for cosine. So I'll just flip that. But I notice in doing so, I have a radical in the denominator. I want to rationalize that. What do I need to multiply the top and bottom of 3 over 2 root 2 to rationalize this? Roman? So you can use 2 root 2, but that's actually more than you need. You'll have some reducing to do after that. All I really need is the radical part. I don't need the entire denominator. I just need the radical piece. I can just do root 2. It's not wrong to do that, but you'll have some reducing to do at the end, guaranteed. If we go this way, we might not. Of course, yes. So again, the numerator I end up with 3 root 2. The denominator I'm going to have 2 times 2. The first 2 is from the 2 on the 2 root 2. The second 2 is from root 2 times root 2. Is everybody okay? I highlighted to kind of emphasize that. I hope that's helpful. Yeah? To see where that's all coming from. And 2 times 2 is just 4. What do you guys think? No big deal? Once you've seen that, oh, I see, I just have to do a little bit of extra setup and then it's back to the same problem as before. If I can do the other one, I can do this one. Should be okay. Questions so far? Am I going too fast? Sometimes I get, this is the second time I'm doing it today, so sometimes I get going. If I feel like it's going too fast, please stop me and be like, hey, can you just slow down a little? Are you going too fast? I will not be upset. I know this is something I do. I'm admitting it to you right now. If I get moving too fast, you're perfectly within your, you should feel obligated or not obligated, but entitled to raise your hand and be like, hey, just slow down a little bit. You're going too fast again? It's like, okay. I know. All right. Another example. So let's say we ask you to find the exact value of sine pi over 6. When we are asked for an exact value of sine, cosine, or tangent, what do we know that we're going to be using here? What tool do we need to use if we're looking for an exact value? Not the calculator. Because we don't want to round it. We don't want a decimal for an exact. We're going to be using a 30, 60, 90 or 45, 45, 90 triangle. So we're going to be stuck doing one of those two. So when we have an exact value for sine, cosine, tangent, etc., we know we're going to be using one of those guys. But Mr. Kulik, those are degrees. I have sine of pi over 6. What the heck is that pi over 6 in there? It's radians. So what's my first order of business going to be? I'm just going to convert that radian measure into a degree measure so I know which stinking triangle to look at. So I'll take pi over 6 in radians and multiply it by 180 over pi. So the sine of pi over 6 is really just the sine of 30 degrees. So if I draw my 30, 60, 90 triangle, oops, that's not. Yee, boyzos. And I write sine of 30, that gives me a over 2a, or just 1/2. Okay there? No big deal, right? Just using the 30, 60, 90 or 45, 45, 90 triangle. And if it's in radians, just convert it to degrees so you know what to do. It's all right? It's all right. All right. What if I ask you to do something like find sine of 17?
Can I go to
Sure. What kind of answer is this what kind of answer are we being asked for? Does it need an exact answer? No. So how the heck am I going to do sine 17? I don't need an exact answer. Decimal's fine. Yeah, just type into the calculator. Before I do that, though, what should I check? Yeah, the mode of my calculator, right? The calculator mode should match the type of angle in my problem. This is 17 degrees before I type in sine 17 into my calculator. I want to make sure I'm in degree mode. I am. I changed it last period, so I knew I was already. But I just type sine 17 and press enter, so I get 0.292. And no big deal there, right? Easy enough. What about secant of 78 degrees? It's cool if there's no secant button on my calculator. What am I supposed to do with that? What other trig function was secant related to? Not sine, cosine. So what I'm going to do is I'm going to do cosine of 78 and then make the reciprocal. So I'm going to do cosine 78. And then if you press this x to the negative 1 button here on the left-hand side, right underneath the math button, that's the reciprocal command. Just does it the flippy. So my answer I'd write is, what? 4.810, rounded to 3 decimal places. Is that cool? No big deal, right? Like punching it in my calculator. Woo! I know. All right. Last example. That should be some good news. You guys all look like have low blood sugar or something. So our last example says solve the triangle. What does the direction solve the triangle mean? That should be a direction we recognize from geometry. Roman?
Find all the sides and angles.
Perfect, yes. Find all the sides and all the angles. Wonderful. In this particular problem, one of those answers is basically free. Which answer is like the basically free part? The angle, right? So let's call that angle x. Ooh, boy. How do we find that angle x? Perfect, yeah. Or even you could just do 90 minus 41, since it's a right triangle. But that's what you said is certainly 100% correct. Everybody's cool? Okay. Let's find the hypotenuse next. I'm going to call that h for hypotenuse. So I'm going to use this 41 degree angle. I'm going to use the other side I know, and I'm going to use h. Which trig function do I need to use here? Cosine, because this side is the adjacent and this is the hypotenuse. So say cosine 41 equals adjacent over hypotenuse. I'll multiply both sides by h to get it out of the denominator, and then divide both sides by cosine 41. And then it's just calculator time, right? Everybody feels okay? I'm going to let you guys punch that through on your own with the calculator. I don't have it sitting in front of me right this second. The other side I'll call L for leg. So again, to calculate that, I'm going to use the 41 degree, the 12, and then this leg, or this side L. What trig function do I want to use to do that? Tangent. Because I have opposite and adjacent. To get the L by itself, I just multiply both sides by 12, and then it's calculator time. Again, I'll let you guys punch that through. I don't have it sitting in front of me. And that's it for these two sections. Again, this second section should be largely, the same thing that we did last time with like a couple of small additions, but it's basically the same thing. So your assignment for sections 1 and 2 is going to be 1 through 42. The problems are all in the OneNote. If you click on the problems page, the OneNote are all here. So you can do your homework in OneNote or on a separate sheet of paper. If you're doing your homework in OneNote, writing it in OneNote, please don't do the following. Okay? Please don't copy the homework problems in and then write your answers little tiny next to the problem. It's fine to have the homework problems on the same page as your work, but have like a separate column on the side that you label like 1, 2, 3 and leave yourself enough room to write and show your work so that it's not like incredibly difficult for Mr. Kulik to kind of follow what the heck you're doing because you left yourself no space to work and it's like a jumbled mess. If you're doing your work on a separate sheet of paper, that is fine. Next time in class, we'll talk about how to get the work from your paper into the place in OneNote where you're turning your homework in. I don't want to do that today because if you have your entire assignment done, we can just practice how to get it with the actual assignment. What is the due date for all homework assignments? Sunday at midnight, except for this one because we don't have school on Monday. It'll be Monday at midnight. So this 1 through 42 is not due till Monday at midnight, so you don't need it prepared for next class. If you do, that's great. If you want to take your time and work on it slowly over the next few days, that's why we've designed it that way. Next class, we'll do another lesson. You'll get another homework. Typically, I want to make sure there's at least one class day before I expect the problem set due. So next class, because we don't meet on Friday this week because there's no school, wouldn't be due until the following Sunday. So we'll meet again on Wednesday, we'll do a homework, and that wouldn't be due until a week from Sunday. And I'll add things into that problem set during next week also, but I always want to try to make sure there's at least one class where if you try the homework and you're confused or you don't know what to do, you'll be able to come back and ask questions before something is due.
Like,
Here.
this homework is due on Monday, but it says it's due the second. The second is Sunday.
Okay, well, I'll update that then.
Yeah, that's what I was
That's
asking
okay.
before.
That's okay.
I
yeah.
knew the homework was due like on Sunday, like this week, but like when I was looking, I'm like, wait, what's the date off of school?
Yep. Max? Of course. But again, you can turn the homework in whenever, right? It doesn't have to be at the deadline. You could do it tomorrow if you want.
We can do it on paper, right?
Yes. I'll show you on next class how to get it from your paper into your OneNote if you're confused. But basically all you're doing is taking a picture with your cell phone, emailing it yourself, and then getting that picture into OneNote.
In my calendar, though,
Right.
it says that
And
we
then it's
have
1 through 42.
Yes.
Wait, do we have Monday off?
Yes.
And then
Oh, wait. And it's due Monday. Well, we have no school Monday.
Right. The homework is always due on Sunday at midnight. Right? Now, because we don't have school on Monday, I've pushed it out another day.
Alright.
Because
I
I won't look at the homework until Tuesday anyway. So like
Oh, okay.
if Sunday at midnight or Monday at midnight makes no never mind to me, like I'm just gonna make it,
The night of.
the night before the school week starts.
I was a little confused. It locked in to my head.
Okay, you got it?
Yeah, but not.
Okay. But that's in general, like, I want to give you lots of time to work on it, to get stuck, to take a break, to not have to be like, oh my God, I have to grind through all this before next class. It's like, like don't work on it so long you get frustrated and you're just going through the motions. Like, quit, take a break, come back. You have time.